Imagine the most violent explosion in the universe. Not a bomb, not a volcano, not anything humans have ever created. Imagine an explosion so powerful that for a brief moment, a single dying star outshines its entire galaxy of hundreds of billions of stars. An explosion that releases more energy in a few seconds than our sun will produce in its entire 10 billion year lifetime. An explosion so bright it can be seen from halfway across the universe. An explosion that creates elements that never existed before and scatters them across space to eventually become planets and life. This is a supernova, and tonight, I want to take you inside one. I want to show you what actually happens during those moments of cosmic violence. Not just the facts and figures, but the process, the sequence of events, the physics that drives it, the beauty hidden in the destruction. Because when you understand what happens during a supernova, when you really grasp the process step by step, it changes how you see everything. It changes how you see the stars, how you see the elements, how you see yourself, because the iron in your blood, the calcium in your bones, the gold in any jewelry you might wear, all of it was forged in supernovae. You are literally made of stardust, created in the most violent events in the cosmos. And understanding how that happens, understanding the process that turns a dying star into an explosion that seeds the universe with the raw materials for life, that's profound, that's meaningful. That connects you to the cosmos in the most direct way possible. So, let's go on this journey together. Let's watch a star die. Let's see what actually happens during a supernova, moment by moment, layer by layer, from the quiet accumulation of iron in the core to the spectacular explosion that lights up the galaxy. Let's understand the physics, the beauty, the significance. Let's see why supernovae are not just interesting astronomical events, but essential processes that make the universe and life possible. Before we can understand how a star dies, we need to understand how it lives. Because a supernova is not a random event. It's the inevitable conclusion to a specific type of stellar life. It's the final chapter in a story that's been unfolding for millions or billions of years. So let's start with what stars are and how they work. A star is, fundamentally, a ball of gas held together by its own gravity. But it's not just sitting there, it's fighting itself. Gravity is trying to crush the star inward, to collapse it into a tiny, dense ball. But the star fights back with pressure, and that pressure comes from nuclear fusion happening in the core. Deep in the center of the star, hydrogen atoms are being crushed together so hard that they fuse into helium. This process releases enormous amounts of energy. This energy heats the star and creates pressure that pushes outward against gravity. So a star is a balance. Gravity pulling in, pressure pushing out. As long as these forces balance, the star is stable. It can shine steadily for millions or billions of years. But this balance requires fuel. It requires hydrogen to fuse, and eventually the hydrogen runs out. Not all at once, not in the entire star, but in the core where the temperature and pressure are highest and fusion happens fastest, the hydrogen gets used up. When that happens, the core contracts. gets denser, gets hotter, and if the star is massive enough, if it has enough gravity to squeeze hard enough, the core gets hot enough to fuse helium into heavier elements, carbon and oxygen, and the star continues living. But here's the key. Not all stars can do this. Small stars like red dwarfs never get hot enough to fuse helium. They just use up their hydrogen over trillions of years and then fade away. Medium stars like our Sun can fuse helium but can't go beyond that. They fuse helium into carbon and oxygen, then puff off their outer layers as a planetary nebula and leave behind a white dwarf. But massive stars, stars with at least 8 times the mass of the Sun, they can keep going. They can fuse heavier and heavier elements. And this is where the story of supernovae begins, with massive stars. Stars that are doomed from birth to die spectacularly. These massive stars burn through their fuel quickly. They shine brightly. They're hot and luminous, but they don't last long. A star like the Sun will live for about 10 billion years. A massive star with 20 times the Sun's mass might live for only 10 million years. 100 times faster, because the more massive the star, the hotter its core, the faster it fuses, and the shorter its life. These stars are living fast and dying young, cosmically speaking. And the way they die is through supernovae. Now, let's follow the life of a massive star from birth to the moment before it explodes. Understanding this progression is crucial because the structure the star develops determines what happens during the supernova. A massive star forms from a cloud of gas and dust that collapses under its own gravity. As it collapses, it heats up. Eventually, the center gets hot enough, about 10 million degrees, for hydrogen fusion to begin. The star ignites. It starts its main life, fusing hydrogen into helium in its core. For a star with 20 times the Sun's mass, this hydrogen burning phase lasts about 10 million years. The star shines brightly. It's a massive, hot, blue star. Life is good, relatively speaking, but eventually the hydrogen in the core runs out. The core is now pure helium, and without fusion to generate pressure, the core contracts. As it contracts, it heats up. Gravity is squeezing it harder, and when the temperature reaches about 100 million degrees, helium fusion begins. Helium fuses into carbon and oxygen. This helium burning phase is shorter, maybe 1 million years for our example star. The star now has a structure like an onion, a carbon-oxygen core surrounded by a shell of helium, surrounded by a shell of hydrogen. And in shells around the core, hydrogen and helium are still fusing. Then the helium in the core runs out. The core contracts again, heats up again, and if it reaches about 500 million degrees, carbon fusion begins. Carbon fuses into neon, magnesium, oxygen. This phase lasts only about 1,000 years. The onion gets another layer, then neon burning, then oxygen burning. Each phase is shorter than the last. Each requires higher temperatures. Each produces heavier elements. Oxygen burning lasts about a year. It produces silicon and sulfur. And then comes silicon burning. Silicon fuses into iron. This is the final phase, and it lasts about 1 week. 1 week. The star has spent millions of years getting to this point, and now it has 1 week left to live. At the end of silicon burning, the core of the star is pure iron, nickel and iron to be precise, and it's incredibly dense and hot. The temperature is billions of degrees. The density is millions of times that of water. The core has grown to about 1.5 times the mass of the Sun, all packed into a sphere roughly the size of Earth, and it's surrounded by layers of silicon, oxygen, carbon, helium, and hydrogen, each layer fusing and creating the elements that will eventually be blasted into space. This is the structure of the star moments before it dies. An iron core surrounded by shells of progressively lighter elements, a cosmic onion that's about to explode. Now we need to understand why iron is special. Why is iron the end of the line? Why can't the star keep fusing iron into heavier elements? The answer has to do with nuclear binding energy. When you fuse light elements like hydrogen and helium, the resulting nucleus has less mass than the original atoms. Mass is converted to energy according to Einstein's famous equation E equals mc squared. This energy is released, and it's what powers the star. But there's a limit. Iron has the most tightly bound nucleus of any element. It has the highest binding energy per nucleon. This means that fusing iron into heavier elements doesn't release energy. It requires energy. Instead of powering the star, fusing iron would drain energy from it. So, when the core becomes iron, fusion stops. There's no more fuel, no more energy source. The star's core is now inert. It's not fusing anything. It's just sitting there, held up by electron degeneracy pressure. This is a quantum mechanical pressure that comes from the fact that electrons can't all occupy the same quantum state. They push back against compression. This pressure is what holds up white dwarfs, and for a moment, it holds up the iron core of our massive star. But there's a limit to how much mass electron degeneracy pressure can support. This limit is called the Chandrasekhar limit, and it's about 1.4 times the mass of the Sun. Our iron core is right at or slightly above this limit. It's balanced on a knife edge, and as silicon continues burning in the shell around the core, more iron is added to the core. The core's mass increases. It edges past the Chandrasekhar limit. And then, catastrophically, electron degeneracy pressure fails. The core can no longer support itself. Gravity wins, and the core begins to collapse. This is the moment. This is the beginning of the supernova, and once it starts, nothing can stop it. The core collapses in less than a second. In a fraction of a second, a core the size of Earth with 1.5 times the mass of the Sun collapses to a ball only 20 kilometers across. It shrinks by a factor of thousands. The matter falls inward at speeds reaching 70,000 kilometers per second. That's 23% of the speed of light. Gravity is pulling everything inward with unimaginable force. The temperature skyrockets. The density becomes enormous. And something strange happens to the electrons. At these extreme densities and temperatures, electrons and protons are squeezed so close together that they undergo a process called electron capture. An electron and a proton combine to form a neutron and release a neutrino. This process removes electrons, which were providing the degeneracy pressure. This accelerates the collapse. The core is now mostly neutrons, packed together as tightly as matter can be packed. It's becoming a neutron star, and at the density of a neutron star, neutron degeneracy pressure kicks in. Neutrons, like electrons, obey quantum rules that prevent them from all being in the same state. They push back hard. The collapse stops, not gradually, but abruptly. The inner core reaches nuclear density about 4 times 10 to the 17th kilograms per cubic meter. That's so dense that a teaspoon of this material would weigh as much as a mountain. And at this density, the neutron degeneracy pressure is strong enough to halt the collapse. But the rest of the core is still falling inward. Material is still raining down at a significant fraction of the speed of light, and it hits the now solid inner core like a hammer hitting an anvil. This collision is so violent, so energetic, that it creates a shockwave, a wave of pressure and energy that propagates outward from the core. This shockwave is the mechanism that will blow the star apart. This is how the supernova begins. The core collapse takes about 1/4 of a second. The shockwave forms and starts moving outward through the infalling material. It's a race. The shockwave is trying to propagate out and blow up the star, but it's fighting against material falling inward, and the shockwave is losing energy. As it passes through the outer core, it has to dissociate iron nuclei into protons and neutrons. This process absorbs energy, millions of ergs per gram. The shockwave weakens. It stalls. About 100 kilometers from the center, the shockwave runs out of energy and stops. At this point, if nothing else happened, the shockwave would fail. The supernova would fizzle. The star would collapse into a black hole without producing the spectacular explosion we observe. But something else does happen. Something saves the supernova. Neutrinos. When the core collapses and neutrons form, vast numbers of neutrinos are released. About 10 to the power of 58 neutrinos in total. This is an unimaginable number, more neutrinos than there are atoms in the sun. And these neutrinos carry away about 99% of the energy released by the collapse. That's about 10 to the 46 joules of energy. For comparison, the sun's total energy output over its entire lifetime is about 10 to the 44 joules. The neutrinos from a supernova carry away 100 times more energy than the sun will produce in its whole life, and they do it in about 10 seconds. Now, neutrinos are weird particles. They barely interact with matter. They can pass through the entire Earth without being stopped. But in the extreme density of the collapsing core, even neutrinos interact occasionally. And there are so many of them, such an intense flux, that even their tiny interaction rate becomes significant. A small fraction of the neutrinos, maybe 1%, deposit their energy in the stalled shockwave region. They heat up the material there, they add energy to the shockwave, and this is what revives it. The shockwave gets a boost of energy from the neutrinos. It starts moving outward again. It accelerates, and now it's strong enough to blast through the outer layers of the star. The shockwave propagates outward through the onion layers, through the silicon shell, through the oxygen shell, through the carbon, helium, and hydrogen. Each layer is blasted outward at speeds of thousands to tens of thousands of kilometers per second. And as the shockwave passes through these layers, something important happens. The extreme temperatures and pressures in the shockwave, which can reach billions of degrees, are high enough to fuse elements. Not just the elements already there, but heavier elements. Elements heavier than iron. Remember, fusing iron requires energy input, but the shockwave has energy to spare. So, in the brief moment as the shockwave passes through the outer layers, rapid fusion occurs. Protons and neutrons are captured by nuclei. Elements all the way up to uranium and beyond are formed. Gold, platinum, silver, lead, all the heavy elements. Everything in the periodic table beyond iron is created in these moments. The shockwave reaches the surface of the star. The star's outer layers are blown off into space at incredible speeds. The explosion releases about 10 to the 44 joules of energy in the form of kinetic energy of the ejected material. And then the light show begins. The material blasted into space is hot, billions of degrees initially. It emits radiation, lots of it, mostly in X-rays at first, but as it expands and cools, the spectrum shifts. After a few hours, the material cools enough that it starts emitting visible light. And this is when we see the supernova. The brightness rises rapidly over a few days. The supernova can outshine its entire galaxy. At peak brightness, a supernova can emit as much light as 5 billion suns. 5 billion. You could see it from millions or billions of light years away. It's one of the brightest events in the universe, and it stays bright for weeks or months, gradually fading as the ejected material expands and cools. The light we see comes from the radioactive decay of unstable isotopes created in the explosion. Nickel-56 decays to cobalt-56, which decays to iron-56. This decay releases energy that keeps the expanding debris hot and glowing for months. Eventually, the supernova fades, but the remnant expands for thousands of years. And what's left behind at the center is the core, the neutron star or black hole that formed during the collapse. Let me take you through the timescale of the explosion in more detail, because the speed is part of what makes it so violent. The star has been living for millions of years, burning hydrogen, helium, progressively heavier elements, building up its onion structure. All of this is stable and relatively slow, but in the final day before the supernova, silicon is burning to create iron in the core. One day, in the final hour, the iron core reaches critical mass. It edges past the Chandrasekhar limit. Electron degeneracy pressure can no longer support it. In the final second, the core begins to collapse. In less than a quarter of a second, the core collapses from the size of Earth to the size of a city. The density increases by a factor of billions. The temperature soars. In the next fraction of a second, the inner core reaches nuclear density and rebounds. The shockwave forms. In the next few seconds, neutrinos are released and revive the stalled shockwave. In the next few minutes, the shockwave propagates through the outer layers of the star. In the next few hours, the shockwave reaches the surface and the star's outer layers are ejected. In the next day, The supernova brightens and becomes visible. In the next weeks, it reaches peak brightness. In the next months, it fades. In the next years and centuries, the remnant expands, glowing as a nebula. In the next thousands of years, the remnant disperses, mixing its enriched material with the interstellar medium. From one day of silicon burning to thousands of years of remnant expansion, the process unfolds on multiple time scales. But the core event, the actual collapse and explosion, happens in about a second. 1 second. That's how long it takes for a star to die. All the build-up, all the millions of years of life, all of it culminates in 1 second of violence that determines the star's legacy. And in that 1 second, the core collapses, rebounds, sends out a shockwave, and begins the process that will scatter the star's enriched material across space. It's fast, it's violent, it's inevitable, and it's beautiful in its own way. The universe taking matter and energy and transforming them. Destruction that leads to creation. A star dying so that new stars and planets and eventually life can form from its ashes. This is the cycle of the cosmos, and supernovae are the key mechanism. They take the hydrogen and helium that filled the early universe and turn it into carbon, oxygen, nitrogen, iron, gold. They create the elements that make planets and life possible, and they scatter these elements across space, seeding the next generation of stars and worlds. So, when you see a supernova, when you read about one in the news or see a picture of a supernova remnant, remember what you're looking at. You're seeing the moment when a star gave everything it had, when it collapsed and exploded and seeded the cosmos with the raw materials for new worlds. You're seeing creation through destruction, rebirth through death. The fundamental cycle that makes the universe interesting and complex and capable of producing life. That's what actually happens during a supernova. A star collapses, the core rebounds, a shockwave forms and is revived by neutrinos. The star explodes, elements are created, material is scattered, and the cosmos is enriched, its physics, its chemistry, its astrophysics at its most extreme. And it's happening somewhere in the universe right now. Right this moment, a star somewhere is reaching the end of its life. Its iron core is growing. The moment of collapse is approaching. And soon, in a fraction of a second, it will explode and light up its galaxy. We can't see it yet. The light hasn't reached us, but it's happening. The universe is full of supernovae. They're rare in any given galaxy, maybe 1 or 2 per century in a typical galaxy like the Milky Way. But there are hundreds of billions of galaxies. So, at any given moment, dozens of stars are exploding somewhere in the observable universe. The cosmos is alive with stellar death and rebirth. And understanding what happens during these events, understanding the mechanism step by step, that's what connects us to the grand cycles of the universe. That's what helps us see our place in the cosmic story. Let me help you understand the physics even more deeply, because when you grasp what's really happening inside that collapsing core, the process becomes even more remarkable. Think about the forces involved. Gravity is pulling everything inward. Every particle of matter in that iron core is being pulled toward every other particle. The combined gravitational force of 1.5 solar masses concentrated in a sphere the size of Earth is enormous. It creates pressures that we can barely comprehend. At the center of the core, the pressure is about 10 to the 30 pascals. That's 10 billion times the pressure at sea level on Earth. It's the kind of pressure where normal matter cannot exist in any form we'd recognize. Atoms are crushed, the electrons are stripped away from the nuclei. What remains is a soup of nuclei and free electrons, all jammed together far more densely than anything found on Earth. The nuclei themselves are mostly iron 56. This is a stable isotope with 26 protons and 30 neutrons. Under normal conditions, these nuclei would be separated by clouds of electrons. But at these densities, the electrons are squeezed into the spaces between nuclei. Everything is compressed together. Now, as the core contracts and the density increases, something has to give. And what gives is the structure of matter itself. The electrons can't keep being squeezed into smaller volumes indefinitely. At some point, they start combining with protons. An electron hits a proton, and they merge to form a neutron plus a neutrino. This reaction is called electron capture. It's energetically unfavorable under normal conditions, but at the extreme densities in the core, it becomes possible. And it has two important effects. First, it removes electrons. This is bad for the core because electrons were providing pressure through electron degeneracy. As electrons disappear, the pressure supporting the core decreases. Second, it creates neutrinos, lots of them. And neutrinos, unlike electrons, don't stick around. They escape from the core, carrying energy away. This cooling further destabilizes the core, so electron capture accelerates the collapse. The more the core contracts, the more electron capture occurs. The more electron capture occurs, the fewer electrons remain to provide pressure. The less pressure there is, the more the core contracts. It's a runaway process. Once it starts, it can't be stopped. The core is doomed. And all of this happens in a fraction of a second. The iron core goes from being marginally stable, held up by electron degeneracy pressure, to collapsing at relativistic speeds almost instantaneously. The transition is violent and sudden. One moment, the core is sitting there, quietly accumulating mass from the silicon burning shell. The next moment, it's collapsing, and nothing can stop it until the neutrons themselves push back. Now, let's think about what happens to the protons and electrons as the core collapses. Initially, the core is made of iron nuclei, which have 26 protons each plus free electrons. As electron capture occurs, the protons are converted to neutrons. The iron nuclei become neutron-rich isotopes, and eventually the nuclei break apart entirely. At the extreme densities reached during the collapse, nuclei can't hold together. The strong nuclear force that binds protons and neutrons into nuclei is overwhelmed by the compression. The nuclei disintegrate into a sea of individual protons and neutrons. This process is called nuclear photodisintegration when photons cause it, but in this case, it's the density itself that tears the nuclei apart. So now you have free neutrons, free protons, and some remaining electrons, all at nuclear density. This is the soup that will become a neutron star. As the collapse continues, more and more protons capture electrons and become neutrons. By the time the core reaches nuclear density and the collapse stops, the composition is about 90% neutrons, 10% protons, and electrons. It's a neutron star being born. And when that inner core reaches nuclear density, when the neutrons are packed as tightly as they can be without touching, neutron degeneracy pressure kicks in. Neutrons are fermions, just like electrons. They obey the Pauli exclusion principle, which says that no two identical fermions can occupy the same quantum state. This creates a pressure, a resistance to further compression. And at nuclear density, this pressure is enormous, strong enough to stop the collapse, dead. The inner core solidifies into a neutron star in a fraction of a second. It goes from collapsing to stable almost instantaneously. But the rest of the core doesn't know this yet. Material farther out is still falling inward at tens of thousands of kilometers per second. It hasn't gotten the message that the core has stopped collapsing, and when it reaches the now solid inner core, it crashes into it. The collision is unimaginably violent. Material moving at 20% of the speed of light hits an immovable object. The kinetic energy of this infalling material is converted into thermal energy and pressure. The temperature spikes to hundreds of billions of degrees. The pressure becomes enormous, and a shockwave forms. This shockwave is a discontinuity, a boundary where the pressure, temperature, and density change suddenly. On one side, material is still falling inward. On the other side, material has been shocked and is now moving outward. The shockwave propagates out from the core, moving through the infalling material. Initially, it's strong. It has a lot of energy. But as it moves outward, it encounters denser and denser material from the outer core, and this material absorbs energy from the shockwave. Here's why. The outer core is still made of iron and other heavy elements. When the shockwave hits these nuclei, it has to break them apart. It has to disintegrate iron into protons and neutrons. This process requires energy. A lot of energy, about 2 MeV per nucleon. For an iron nucleus with 56 nucleons, that's about 100 MeV. Multiply this by the enormous number of nuclei in the outer core, and you get a staggering energy drain. The shockwave loses energy fast. Within a fraction of a second, the shockwave has propagated about 100 to 200 kilometers from the core, and at this point, it stalls. The energy loss from photodisintegrating nuclei has sapped its strength. The shockwave is no longer moving. It's stuck in the outer core, neither advancing nor retreating. And if this were the end of the story, the supernova would fail. The core would continue to accrete matter. It would grow more massive, and eventually it would collapse into a black hole, swallowing everything without producing the explosion we observe. But there's a mechanism that saves the supernova: neutrinos. During the collapse, vast numbers of neutrinos were created, some from electron capture, some from the extreme temperatures allowing pair production of neutrino-antineutrino pairs. These neutrinos carry away most of the gravitational binding energy released by the collapse. That's about 3 times 10 to the 46 joules, and while most neutrinos escape without interacting, a small fraction do interact with matter. Neutrinos have a tiny interaction cross-section. Under normal conditions, they can pass through light years of lead without being stopped. But in the extreme density of the supernova core, even their tiny interaction probability becomes significant. The neutrino flux is so intense, about 10 to the 57 neutrinos per square centimeter per second, that even a small interaction rate adds up. About 1% of the neutrinos deposit their energy in the region just behind the stalled shockwave. They scatter off nuclei and electrons. They transfer momentum and energy, and this energy heats the material in the gain region, the zone between the neutron star surface and the stalled shockwave. This heating creates convection. Hot material rises, cool material sinks, the gain region churns, and this convection helps transport energy from the neutron star surface, where neutrinos are being emitted, to the stalled shockwave. The energy input from neutrinos is slow. It takes about 100 milliseconds to a second for enough energy to accumulate. But eventually, the shockwave gets the boost it needs. It revives. It starts moving outward again, and now, with renewed energy, it's strong enough to blast through the rest of the star. This neutrino-driven mechanism is the current understanding of how supernovae work. It's not fully understood. Simulations are complex and require massive supercomputers. But the basic idea is that the shockwave stalls. Neutrinos revive it, and then it blows up the star. This process is delicate. If the neutrino luminosity is too low, or if the mass of the core is too high, the shockwave won't revive. The supernova will fail. This might be what happens to the most massive stars. They collapse directly to black holes without producing supernovae. But for stars in the right mass range, about 8 to 25 times the Sun's mass, the mechanism works. The neutrinos save the day. The shockwave revives and the star explodes. Now think about what happens as the shockwave propagates outward through the star. It's moving at speeds of thousands to tens of thousands of kilometers per second. It passes through the layers of silicon, oxygen, carbon, helium, and hydrogen. Each layer is heated to billions of degrees by the shockwave, and at these temperatures, nuclear reactions occur. Rapid neutron capture happens. Free neutrons, created in the shock, are captured by nuclei. A nucleus captures a neutron, becomes a heavier isotope. If that isotope is unstable, it beta decays, turning a neutron into a proton and emitting an electron and antineutrino. Then another neutron is captured. This process, called the R process for rapid neutron capture, creates heavy elements beyond iron, all the way up to uranium and even heavier. The R process requires extreme conditions: high neutron density, high temperature, short timescale. These conditions exist in the supernova shockwave and in the neutrino-heated ejector. This is where most of the universe's gold, platinum, and uranium come from. Supernovae, the explosions of massive stars. There's also another process called the S process, slow neutron capture, which occurs in aging stars before they explode. But the R process in supernovae is responsible for about half of the elements heavier than iron. Every gold atom in your jewelry was created in a supernova. Every uranium atom in nuclear fuel was forged in the extreme conditions of a stellar explosion. These elements didn't exist in the early universe. They were created by stars, and they were dispersed by supernovae. Without supernovae, the universe would be mostly hydrogen and helium. There would be no rocky planets, no heavy elements, no complex chemistry, no life. Supernovae are the mechanism that enriches the cosmos, that takes the simple elements created in the Big Bang and stellar cores and transforms them into the full periodic table. And they scatter these elements across space, mixing them with the interstellar medium, making them available for the next generation of stars and planets. This is cosmic recycling, matter flowing from the Big Bang to stars to supernovae to new stars to planets to life, and potentially back to stars again. A grand cycle driven by gravity, fusion, and explosion. And supernovae are the critical step. They're the distribution mechanism, the cosmic seed spreaders. Let me also help you visualize the scale of energies involved, because the numbers are so large they become abstract. The energy released by a supernova is about 10 to the 46 joules. To put this in perspective, the Sun's total luminosity, the energy it emits per second, is about 4 times 10 to the 26 watts. That's 4 times 10 to the 26 joules per second. The Sun has been shining for about 4.6 billion years. That's about 1.5 times 10 to the 17 seconds. Multiply these together, and the Sun has emitted about 6 times 10 to the 43 joules in its entire life so far. A supernova releases about 1,000 times more energy than this in a few seconds. If you could capture the energy from a supernova and convert it to electricity, it would power human civilization at current usage rates for about 10 to the 32 years. That's a trillion years. Far longer than the current age of the universe. It's an unimaginable amount of energy, and it's released almost instantaneously. Most of it, 99%, is carried away by neutrinos. Only about 1% goes into the kinetic energy of the ejected material and the light we see. But even 1% of 10 to the 46 joules is 10 to the 44 joules. Still 1,000 times the Sun's total lifetime output. That's how violent supernovae are. That's how much energy is liberated when a massive star's core collapses. And this energy does multiple things. It accelerates the star's outer layers to thousands of kilometers per second. It heats the ejector to billions of degrees. It powers nuclear reactions that create heavy elements. It produces the light show that can outshine a galaxy. And it leaves behind a neutron star or black hole, an exotic remnant that will persist for billions of years. All from 1 second of core collapse. 1 second where gravity, having been fought to a standstill by fusion pressure for millions of years, finally wins. 1 second where a star's core collapses and rebounds and sends out a shockwave that tears the star apart. It's the most energetic event associated with the death of a star. More energetic than anything else, except perhaps the merger of two neutron stars, or a neutron star and a black hole. Supernovae are among the most luminous, most energetic, most significant events in the universe, and they happen regularly. In a galaxy like the Milky Way, about 1 to 3 supernovae occur per century on average. That might not sound like many, but over the billions of years of the galaxy's history, that's millions of supernova. Millions of stars that have lived and died and scattered their ashes into space. And every one of those supernovae contributed to the chemical enrichment of the galaxy. Every one added heavy elements to the interstellar medium. Every one made the galaxy a little richer, a little more complex, a little more capable of forming rocky planets and potentially life. Our solar system formed from a cloud of gas and dust that had been enriched by previous generations of stars. The elements heavier than helium in that cloud came from earlier supernovae. The iron in Earth's core, the oxygen in the atmosphere, the carbon in living things, all of it came from stars that died before the sun was born. We're made of recycled stardust. And the recycling mechanism is supernovae. This is not metaphor. This is not poetic language. This is literal truth. The atoms in your body were forged in the cores of massive stars and scattered by supernovae billions of years ago. You are physically made of the remnants of stellar explosions. And understanding what happens during a supernova helps you appreciate this connection, helps you see that you're not separate from the cosmos. You're part of it, made from it, connected to it in the most fundamental way through the very substance of your being. This is what supernovae give us, not just a spectacular light show, not just an interesting astrophysical phenomenon, but the raw materials for complexity, for planets, for life. They're the forges where heavy elements are created, the explosions that scatter those elements, the mechanism that makes the universe interesting. Without supernovae, the universe would be a simpler place. Hydrogen and helium, maybe some lithium, but nothing else. No rocky planets, no iron cores, no oceans, no life. Supernovae made all of that possible. They're essential to the cosmic story, essential to the story of life, essential to your story. Because without the supernovae that occurred billions of years ago in the region of space that would eventually become our solar system, you wouldn't exist. The atoms you're made of wouldn't exist. Earth wouldn't exist in its current form. Life couldn't have arisen. Supernovae are not just interesting, they're necessary. They're the mechanism that transforms a simple universe into a complex one. And that's profound, that's meaningful, that's worth understanding in detail. Let me take you even deeper into the moment of explosion, because there's so much happening in those first few seconds that deserves attention. When the shockwave revives and begins its journey outward through the star, it's encountering different conditions in each layer. The silicon layer, closest to the core, is dense and compact. The shockwave moves through it relatively quickly because this layer is thin. But as it does, it heats the silicon to billions of degrees. At these temperatures, the silicon undergoes explosive nucleosynthesis. It fuses into heavier elements in seconds rather than the week it would have taken under normal stellar burning. This creates more iron peak elements: nickel, cobalt, iron. These radioactive isotopes, particularly nickel-56, will play a crucial role later in powering the light curve of the supernova. Then the shockwave hits the oxygen layer. This layer is thicker, more massive. The shockwave slows down slightly as it plows through, but again, it heats the material to extreme temperatures. Oxygen fuses into silicon, sulfur, other elements. The nucleosynthesis continues. Each layer the shockwave passes through undergoes rapid fusion. Elements are created that would never have formed during normal stellar burning, because the shockwave provides conditions, temperature, and pressure that are far more extreme than what exists during stable fusion. As the shockwave moves outward, it's also expanding. The shock front is growing in radius, and as it expands, it encompasses more and more mass. By the time it reaches the outer layers of the star, the hydrogen and helium envelopes, the shockwave has weakened somewhat, but is still powerful enough to accelerate this material to thousands of kilometers per second. The hydrogen envelope, if the star still has one, is blown off entirely. This material will become the expanding debris field, the supernova remnant that we can observe for thousands of years after the explosion. Now let's think about what happens from an observational standpoint. The explosion occurs deep inside the star. The shockwave is propagating outward, but initially we can't see anything. The star looks normal. It's still shining with its pre-supernova luminosity. But beneath the surface, the shockwave is racing outward. It takes time for the shockwave to reach the surface. For a red supergiant star, which is a common endpoint for massive stars, the radius might be several hundred times the Sun's radius. That's enormous. The Sun's radius is about 700,000 kilometers. A red supergiant might have a radius of 100 million kilometers or more. The shockwave is moving at, let's say, 10,000 kilometers per second. Dividing the radius by the speed gives you the time for the shockwave to reach the surface. About 10,000 seconds, a few hours. So, a few hours after the core collapse, the shockwave reaches the surface of the star. It breaks through, and suddenly the star's luminosity begins to rise. The outer layers are heated to extreme temperatures by the shockwave. They emit copious radiation. Initially, this radiation is in the ultraviolet and X-ray parts of the spectrum because the temperature is so high. But as the material expands and cools, the spectrum shifts toward visible light. Within a day or so, the supernova becomes visible to optical telescopes. The brightness rises rapidly. Over a few days, the supernova can become as bright as its entire host galaxy. This is called the shock breakout. It's the moment when the shockwave emerges from the star's surface, and if you happen to be watching the star at exactly the right moment, you can catch this event. It's brief, lasting only a few hours at most, but it's incredibly bright in X-rays and ultraviolet. Some supernovae have been caught during shock breakout by telescopes that monitor large areas of sky continuously. And observing shock breakout gives us unique information about the star's radius, its envelope structure, and the energy of the explosion. After shock breakout, the supernova enters its plateau phase if it's a Type II supernova with a hydrogen envelope. The light curve stays relatively bright for weeks to months. This plateau is powered by the recombination of hydrogen. As the ejecta expand and cool, hydrogen ions recombine with electrons to form neutral hydrogen. This process releases energy that keeps the supernova bright. Eventually, the hydrogen recombines completely and the plateau ends. The light curve drops, but then it stabilizes again, powered by radioactive decay. The nickel-56 created in the explosion has a half-life of about 6 days. It decays to cobalt-56, which has a half-life of about 77 days, and cobalt-56 decays to stable iron-56. Each decay releases gamma rays. These gamma rays heat the expanding ejector, keeping it glowing, and this is what powers the light curve for months after the explosion. The amount of nickel-56 created in the explosion determines how bright the supernova is during this phase. More nickel means more radioactive energy, means a brighter supernova. By measuring the brightness, astronomers can estimate how much nickel-56 was produced, which tells them about the conditions in the explosion. All of this information, the rise time, the peak brightness, the shape of the light curve, the spectrum, all of it gives us clues about what happened during the supernova. It's like forensic science. We're reconstructing the explosion from the light and the debris, and every supernova is slightly different. Each one tells us something about the star that exploded, the mechanism that drove the explosion, and the elements that were created. Now, let me help you understand why studying supernovae matters beyond just satisfying curiosity. Supernovae are tools. They're cosmic laboratories where we can study physics under conditions we can never replicate on Earth. The densities, temperatures, and energies involved are far beyond anything achievable in laboratories. Nuclear physicists study supernova nucleosynthesis to understand how elements are created. Particle physicists study neutrino emission to learn about neutrino properties. General relativists study the collapse of the core to understand gravity in extreme conditions. Supernovae are test beds for fundamental physics, but they're also practical tools for astronomy. Type Ia supernovae, which we'll talk about more later, are standardizable candles. They have a consistent peak brightness, or at least one that can be calibrated. This makes them incredibly useful for measuring distances in the universe. If you know how bright something really is, and you measure how bright it appears, you can calculate how far away it is. Type Ia supernovae can be seen across billions of light years, and by measuring their distances and comparing them to the redshifts of their host galaxies, astronomers can map out the expansion history of the universe. This is how we discovered that the expansion of the universe is accelerating, that there's dark energy pushing the universe apart. Two teams measured distant Type Ia supernovae in the late 1990s and found that they were dimmer than expected. This meant they were farther away than expected for their redshifts, which meant the universe's expansion had accelerated at some point in the past. This discovery won the Nobel Prize in Physics in 2011, and it all came from studying supernovae. So, supernovae are not just interesting events. They're crucial tools for understanding the universe. They tell us about stellar evolution, about nucleosynthesis, about the chemical enrichment of galaxies, about the distances to faraway galaxies, about the expansion of the universe, about dark energy. They're some of the most informative events in all of astronomy, and they're happening all the time. Every day, somewhere in the universe, a star is exploding. We can't see most of them because they're too far away or obscured by dust or pointed away from us. But surveys are finding hundreds of supernovae every year. Amateur astronomers discover them. Professional surveys using automated telescopes find them. Follow-up observations with large telescopes study them in detail. The data accumulates, and our understanding improves. We're learning more about supernovae every year, about how they work, about what stars produce them, about what they leave behind, about how they affect their surroundings. It's an active, vibrant field of research, and it's driven by the fact that supernovae are important. They're not just pretty pictures, they're fundamental to the cosmic story. They're the mechanism that makes the universe rich and complex. They're the forges of heavy elements, the distributors of chemical wealth, the drivers of galactic evolution. Understanding supernovae is understanding how the universe works, how it evolved from the simple hydrogen and helium of the Big Bang to the complex element-rich cosmos we see today. And that understanding connects you to the universe in a profound way. When you know that the iron in your blood came from a supernova, when you understand the process that created it, the star that fused lighter elements up to iron and then exploded and scattered that iron into space, you're connected to that star, connected to that explosion, connected to the cosmos. You're not separate. You're part of the story, part of the cycle, made from the ashes of dead stars. And there's something deeply meaningful about that, something that should change how you see yourself and your place in the universe. You're not just on Earth, you're in the universe, made of it, connected to it, part of its history and its ongoing evolution. Supernovae make that connection concrete. They're the link between the cosmos and you, the mechanism that took matter from stars and eventually turned it into planets and life. And understanding what happens during a supernova helps you appreciate that link, helps you see that you're cosmically significant not because you're special or unique, but because you're made of the same stuff as everything else. You're part of the pattern, part of the cycle. Star stuff that became aware of itself and capable of understanding where it came from. That's what supernovae give us. Not just light and energy and heavy elements, but connection, understanding, perspective, a sense of place in the vast cosmos. And that's worth far more than any scientific discovery. That's transformative. That's profound. That's what makes studying supernovae meaningful on a personal level. Let me give you one more perspective on supernovae that I think is important. The perspective of time. We've talked about how the core collapse happens in a second, how the shockwave takes hours to reach the surface, how the light curve evolves over weeks and months. But zoom out. Think about the lifetime of the star, and massive star with 20 times the sun's mass lives for about 10 million years. 10 million years of stable hydrogen burning, then 1,000,000 years of helium burning, then 1,000 years of carbon burning, then a year of oxygen burning, then a week of silicon burning, then a second of core collapse. The life of the star is a countdown, each phase shorter than the last, each burning stage consuming fuel faster and faster. And It all ends in one moment of violence that undoes millions of years of gradual accumulation. But from another perspective, that moment of violence is the point. The supernova is not the end of the star's story, it's the culmination. The purpose, if stars can be said to have purposes. The massive star existed to create heavy elements and disperse them. It spent millions of years slowly building up layers of progressively heavier elements. And then, in one moment, it scattered all of that wealth into space. Mission accomplished. The star lived and died so that the next generation could be richer, so that new stars forming from the enriched interstellar medium would have access to heavy elements, so that rocky planets could form, so that life could eventually arise. The supernova is not destruction for its own sake. It's creative destruction. It's recycling. It's the universe taking matter and energy and transforming them into something more complex, and then distributing that complexity widely so it can be used again. This is the cosmic cycle, simple to complex, dispersed to concentrated, concentrated to dispersed again, energy flowing, matter transforming, the universe evolving from simplicity toward complexity through countless cycles of stellar birth and death. And we're part of that cycle. We're here, alive, aware, because stars lived and died billions of years ago. Because supernovae scattered the heavy elements that eventually became Earth and everything on it. Because the universe is generous, constantly recycling matter and making it available for new structures, new complexity, new possibilities. When you understand supernovae, when you really grasp what happens and why it matters, you see the universe differently. You see it as dynamic, alive, constantly changing and evolving. Not a static stage on which events play out, but an active participant. A system that creates complexity through its own processes: gravity, fusion, explosion, recycling. These mechanisms, playing out over and over billions of times, in billions of galaxies, over billions of years, are what made the universe interesting, what made it complex, what made it capable of producing beings who can understand it. And you're one of those beings, made of supernova debris, aware of your cosmic origins, capable of understanding the process that created you. That's extraordinary. That's meaningful. That's what I want you to take away from understanding supernovae. Not just the physics, though the physics is beautiful. Not just the violence, though the scale is staggering. But the meaning, the connection, the realization that you're made of stars, that your atoms were forged in stellar cores and scattered by explosions that outshone galaxies, that the universe is not separate from you, you're part of it, intimately, fundamentally, physically part of it. And supernovae are the mechanism that made that possible. The process that turned hydrogen into heavy elements, and those heavy elements into planets, and those planets into homes for life. You are the universe experiencing itself. Star stuff that became conscious, and supernovae are part of your origin story. They're part of what made you possible. So when you hear about a supernova, when you see a picture of a supernova remnant, remember what you're looking at. You're seeing your cosmic heritage. You're seeing the process that created the raw materials for your existence. You're seeing destruction and creation intertwined, death and birth happening simultaneously. a star dying so that you could eventually be born. That's what actually happens during a supernova. A star collapses, explodes, creates elements, scatters them into space, enriches the cosmos. And billions of years later, some of that enriched material becomes you. It's physics, it's chemistry, it's astrophysics, and it's deeply, profoundly, personally meaningful. That's what I wanted you to understand. That's the journey we've taken together through the life and death of a massive star. And we're not done yet, because there's so much more to explore. Different types of supernovae, what they leave behind, famous examples throughout history, how they affect life. All of that is coming. But I wanted to make sure you understood the core process first. The collapse, the rebound, the shockwave, the neutrinos, the explosion, the creation of elements, the scattering of enriched material, the cycle that makes the universe rich and complex and capable of producing life. That's the foundation. That's what actually happens during a supernova, and it's beautiful and violent and necessary all at once. Different types of supernovae tell different stories. Core collapse supernovae, what we've been discussing, come from massive stars. But there's another type Ia supernovae, and they happen through a completely different mechanism. Type Ia supernovae involve white dwarfs. These are the remnants of medium-sized stars like our Sun. When a Sun-like star exhausts its hydrogen and helium fuel, it can't fuse carbon. Not massive enough. The core contracts, becoming a white dwarf, an Earth-sized ball of carbon and oxygen supported by electron degeneracy pressure. About half the Sun's mass compressed into a volume the size of Earth, incredibly dense, but stable. These white dwarfs can last billions of years, slowly cooling. But if a white dwarf is in a binary system with a companion star, something interesting can happen. If the companion is close enough, the white dwarf's gravity can pull matter from it. Hydrogen flows from the companion onto the white dwarf, accumulates on its surface. The white dwarf's mass increases. And remember the Chandrasekhar limit, 1.4 solar masses. That's the maximum mass electron degeneracy pressure can support. As the white dwarf accretes matter, it approaches this limit, and when it reaches it, catastrophe strikes. The white dwarf can no longer support itself. It begins to collapse. But unlike a massive star's iron core, a white dwarf is made of carbon and oxygen, and carbon fusion releases energy. As the white dwarf compresses, the core temperature rises. Carbon starts fusing, and because the white dwarf is degenerate, there's no temperature regulation. In a normal star, if fusion increases, temperature rises, pressure increases, the star expands, and fusion slows. Negative feedback. Stable. But in degenerate matter, pressure doesn't depend on temperature. So when fusion starts, temperature rises, fusion rate increases exponentially. Temperature rises more, and you get runaway fusion, a thermonuclear explosion. The entire white dwarf, 1.4 solar masses of carbon and oxygen, undergoes explosive fusion in about a second. The star doesn't just blow up, it detonates. fusion propagates through the entire white dwarf faster than the speed of sound in the material. In moments, most of the carbon and oxygen fuses into iron peak elements: nickel, cobalt, iron. The energy released is enormous, about 10 to the 44 joules, comparable to core collapse supernovae. The white dwarf is completely destroyed. Nothing left behind. No neutron star, no black hole, just expanding debris. And because every type Ia supernova comes from a white dwarf at the Chandrasekhar limit, they all have roughly the same mass, same fuel, same explosion energy, same peak brightness. This makes them standardizable candles. With careful calibration accounting for minor variations, Type I supernovae can be used as distance indicators. Their consistent brightness allows astronomers to calculate distances to their host galaxies. This is how we discovered dark energy, by measuring Type Ia supernovae in distant galaxies. What remains after a supernova depends on the progenitor star's mass. For stars between 8 and about 25 solar masses, core collapse leaves a neutron star, the compressed core that stopped the collapse, about 1.4 to 2 solar masses packed into a sphere 20 kilometers across. Neutron stars are extraordinary objects. Density approaches nuclear density. A teaspoon of neutron star material would weigh 1 billion tons. The surface gravity is about 2 times 10 to the 11 times Earth's, so strong that if you dropped an object from 1 meter height, it would hit the surface at millions of meters per second. The escape velocity is about half the speed of light. Neutron stars rotate rapidly. Some spin hundreds of times per second. This rotation comes from conservation of angular momentum. The core that collapsed was rotating slowly, but as it shrank by a factor of thousands, it spun up, like a figure skater pulling in their arms. And neutron stars have intense magnetic fields, trillions of times stronger than Earth's magnetic field. These fields are generated by the conducting material and amplified during collapse. The combination of rapid rotation and strong magnetic fields makes some neutron stars visible as pulsars. Beams of radio waves are emitted from the magnetic poles. As the neutron star rotates, these beams sweep across space like a lighthouse. If Earth happens to lie in the path of one of these beams, we detect regular pulses of radio waves. Pulses with periods ranging from milliseconds to seconds. Incredibly regular, more precise than atomic clocks over short timescales. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell. She noticed regular radio pulses coming from a point in the sky. Initially, the regularity was so striking that they considered the possibility of an artificial signal. They jokingly called the source LGM-1 for Little Green Men, but soon more pulsars were discovered, and the explanation became clear. These were rotating neutron stars, not aliens. Pulsars are invaluable tools for studying physics. The extreme conditions in neutron stars allowed tests of general relativity and nuclear physics impossible elsewhere. Some pulsars are in binary systems with other neutron stars or white dwarfs. As these objects orbit, they emit gravitational waves, energy carried away by ripples in space-time. This causes the orbits to decay. The objects spiral together, eventually merging. The first indirect detection of gravitational waves came from observing the orbital decay of a pulsar binary system. The system PSR B9933Pla16, discovered in 1974, showed exactly the decay rate predicted by general relativity. This won the Nobel Prize in Physics in 1993. And when neutron stars finally merge, they produce gravitational waves strong enough to detect directly. LIGO and Virgo gravitational wave detectors have observed several such mergers. The collision also produces a kilonova, an explosion powered by the decay of heavy elements synthesized during the merger. These elements, especially gold and platinum, are created through rapid neutron capture in conditions even more extreme than supernovae. Neutron star mergers might be the primary source of the heaviest elements in the universe. For stars more massive than about 25 solar masses, the core collapses beyond even neutron degeneracy pressure's ability to resist. The core becomes a black hole. When this happens, no explosion occurs, or rather, a much weaker explosion. Maybe. The details are uncertain. These failed supernovae might produce faint optical transients, or they might be invisible. The star simply winks out, disappears. Its outer layers fall into the newly formed black hole. No bright supernova, no scattered debris, just a black hole left behind. This has implications. It means the most massive stars might not contribute as much to chemical enrichment as we thought. If they collapse directly to black holes without ejecting their outer layers, the heavy elements they created remain trapped, never recycled, lost from the cosmic cycle. We're still studying how common failed supernovae are. Observations suggest they happen. Some stars expected to explode have simply vanished from images. They're 1 year, gone the next. No supernova detected, just absence. A black hole probably formed, silent, invisible, and the star's matter fell in. But even when massive stars do explode, what's left is a black hole. The core collapsed past the point of no return, past the event horizon, into a singularity where physics as we know it breaks down. These stellar mass black holes have masses from about 3 solar masses up to dozens of solar masses. They're small compared to the supermassive black holes at galactic centers, but still exotic, still fascinating. And, like neutron stars, black holes in binary systems can eventually merge. These mergers produce gravitational waves. LIGO has detected several black hole mergers. The collisions release more energy than all the stars in the visible universe combined. For a fraction of a second, gravitational wave astronomy is revealing a population of black holes we didn't know existed, masses and configurations that were unexpected, teaching us about stellar evolution in ways optical astronomy never could. Supernova remnants are visible for thousands of years after the explosion. The expanding debris glows, initially heated by the shockwave, later powered by radioactive decay, eventually cooling but still moving outward, sweeping up interstellar gas, creating complex structures. The Crab Nebula is a famous example. a supernova observed in 1054 AD by Chinese and Arab astronomers, visible in daylight for weeks. Today, nearly 1,000 years later, the remnant spans about 11 light-years, still expanding, still glowing. At its center is a pulsar, the neutron star left behind, spinning 30 times per second, emitting beams of radiation, powering the nebula's emission through a wind of high-energy particles. The Crab Nebula looks like a tangled web of glowing gas, filaments of different colors representing different elements: red from hydrogen, blue-green from oxygen. The structure is complex, chaotic, shaped by magnetic fields and turbulence. Cassiopeia A is another young supernova remnant. The star exploded around 1680, though no one on Earth recorded seeing it, probably obscured by dust. Today, Cass A is one of the brightest radio sources in the sky. The debris is expanding at thousands of kilometers per second. X-ray observations show hot gas at millions of degrees. Infrared observations reveal dust forming in the cooling ejector. And there's a neutron star at the center, possibly the youngest known neutron star in our galaxy. These remnants are laboratories for studying supernova physics. We can measure the composition of the debris, see what elements were created, trace the dynamics of the explosion, understand how energy is transferred from the expanding material to the surrounding interstellar medium. Over thousands of years, supernova remnants fade and disperse. The debris mixes with interstellar gas, enriching it, making it available for future star formation. This is how galaxies become enriched with heavy elements. Each supernova adds a bit more. Over billions of years, the cumulative effect is substantial. The interstellar medium becomes progressively richer in carbon, oxygen, iron, all the elements created in stars. And when new stars form from this enriched material, they start with a higher metallicity, more heavy elements. This affects their evolution, and the planets that form around them have more heavy elements too. Rocky planets can form more easily. Complex chemistry is possible. Life becomes more likely. Supernovae affect their surroundings dramatically. The shockwave from a supernova, traveling at thousands of kilometers per second, plows into the interstellar medium, sweeps up gas, compresses it. This compression can trigger new star formation. Dense clumps of gas, compressed by the shockwave, become gravitationally unstable, collapse, form new stars. So supernovae seed their own replacements. They trigger the birth of the next generation of stars. This is a self-perpetuating cycle. Stars form, live, die, explode, trigger new star formation. The process continues. Galaxies evolve through this cycle. Star formation rates ebb and flow. Regions of active star formation are seeded by previous generations. The Orion Nebula, a famous star-forming region visible to the naked eye, might have been triggered by an ancient supernova. Its shockwave compressed the gas that eventually collapsed to form the young stars we see today. Supernovae also create structure. They blow bubbles in the interstellar medium, hot, low density, cavities surrounded by shells of compressed gas. These bubbles can be hundreds of light years across. Multiple supernovae in a region can create superbubbles. Even larger cavities. The Milky Way's disk is filled with these structures. They shape the distribution of gas, influence where new stars form, drive turbulence, maintain the energy balance of the interstellar medium. Without supernovae, galaxies would be different, calmer, more uniform, less structured. Star formation would proceed differently. The interstellar medium wouldn't be stirred and energized. Heavy elements wouldn't be dispersed as efficiently. Supernovae are not just endpoints of stellar evolution, they're drivers of galactic evolution. Historically, supernovae visible from Earth have been rare and significant. Before telescopes, only supernovae in our galaxy or nearby could be seen, and even then, only if they were bright enough and positioned favorably. The historical record includes several notable supernovae. In 185 AD, Chinese astronomers recorded a guest star that appeared in the constellation we call Centaurus. Visible for months, modern astronomers have identified the remnant RCW86. It's faint now, but 1,300 years ago, it was a bright new star in the sky. In 1054, the supernova that created the Crab Nebula appeared. It was visible in daylight, brighter than Venus. Chinese and Arab astronomers recorded it in detail. European records are sparse, possibly because of political turmoil. But the event was unmistakable, a new star where none had been before. In 1572, Tycho Brahe observed a supernova. He measured its position carefully, noted that it showed no parallax, proved it was farther than the moon. This was important because Aristotelian cosmology held that the heavens were unchanging. Tycho's supernova was new, a change in the celestial realm. It challenged old ideas, helped pave the way for the scientific revolution. The remnant of Tycho's supernova is still visible today. Expanding bubble of debris. In 1604, Johannes Kepler observed another supernova, the last supernova visible to the naked eye in our galaxy. Kepler's supernova appeared in the constellation Ophiuchus, brighter than Jupiter at its peak, visible for over a year. Kepler wrote extensively about it, used it to argue against the unchanging heavens. The remnant is studied today with X-ray and infrared telescopes. Since 1604, no supernova has been visible to the naked eye in the Milky Way. We're overdue. Statistical estimates suggest 1 to 3 supernovae per century in a typical galaxy. It's been over 400 years. Maybe the next one is imminent, or maybe it'll be centuries more. We don't know, but when it happens, it'll be spectacular. A new bright star appearing suddenly, possibly brighter than any star in the sky, visible for weeks or months. Astronomers around the world will turn their telescopes toward it, study it in detail, learn more about supernova physics than ever before. Because modern instruments are far more capable than anything available in the past, we'll get spectra, measure velocities, track the evolution of the explosion, detect neutrinos if we're lucky, map the remnant as it forms. It'll be one of the most studied astronomical events in history. The nearest stars, massive enough to go supernova, are dozens of light years away. Betelgeuse, a red supergiant in Orion, is about 540 light-years distant. It's nearing the end of its life. Could go supernova any time. Tomorrow or 100,000 years from now. We don't know. When it does, it'll be incredibly bright. possibly visible during the day, casting shadows at night, but it's far enough that it won't harm Earth. Supernovae need to be within about 30 light years to pose a threat, and there are no massive stars that close, so we're safe. But astronomers eagerly await Betelgeuse's demise. It'll be the closest supernova in centuries, visible to everyone on Earth. A cosmic event generations will remember. Another candidate is Eta Carinae, a hypergiant star about 7,500 light-years away. It's a variable star, erupts periodically. In the 1840s, it briefly became the second brightest star in the sky. Not a supernova, just an outburst. But it's unstable, massive. Probably will explode someday, maybe soon on cosmic timescales. When it does, it might be visible even from that distance. Supernovae can be seen from millions of light-years away. Eta Carinae is much closer. The rate of supernovae in the universe is staggering. Billions of galaxies, each hosting a few supernovae per century on average. That means tens of supernovae per second across the observable universe. Right now, as you read this, dozens of stars are exploding, their cores collapsing, shockwaves propagating, light beginning its journey across space. We'll see some of these supernovae eventually, years or millennia from now, depending on distance. Others will never be visible from Earth, obscured, pointed away, too distant. But they're happening, constantly. The universe is alive with stellar death, and every one of those supernovae enriches its galaxy, creates heavy elements, distributes them, seeds the next generation of stars and planets. The process is ongoing, universal, fundamental to how the cosmos evolves. Supernova progenitors are diverse. We've focused on massive stars, but Type Ia supernovae involve white dwarfs, and there might be other mechanisms. Pair instability supernovae are predicted for extremely massive stars, above about 130 solar masses. In such stars, the core becomes so hot that photons have enough energy to spontaneously create electron-positron pairs. This removes thermal pressure. The core becomes unstable, collapses. But unlike normal core collapse, the entire star is obliterated. No remnant, no neutron star or black hole, just complete destruction. These supernovae might be more common in the early universe, when low metallicity stars could grow extremely massive. We haven't definitively observed one yet, but candidates exist. Hyperluminous supernovae, far brighter than typical, possibly pair instability events. Confirming them would validate predictions about stellar evolution in extreme mass ranges. Superluminous supernovae are exceptionally bright, 10 to 100 times more energetic than typical supernovae. We're still figuring out what causes them. One idea is magnetar formation. If the neutron star left behind is spinning extremely rapidly and has an ultra-strong magnetic field, it could pump energy into the explosion, power the light curve for months, make the supernova extraordinarily bright. Another idea involves interaction with circumstellar material. If the star lost significant mass before exploding, creating a dense shell of gas around it, the supernova ejector slamming into this shell could produce extra luminosity, shock interaction powering the brightness. Both mechanisms might operate. Different superluminous supernovae might have different causes. We're learning as we observe more. Neutrino detection from supernovae is rare. Only one has been detected so far. Supernova 1987 A in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, about 160,000 light-years away. On February 23, 1987, 3 neutrino detectors on Earth, Kamiokande in Japan, IMB in the United States, and Baksan in Russia, detected bursts of neutrinos within seconds of each other. About 24 neutrinos total across all detectors, a tiny fraction of the 10 to the 58 that passed through Earth. But enough. The neutrinos arrived about 3 hours before the optical brightening. This makes sense. The neutrinos escaped the core immediately. The light took hours to emerge as the shockwave reached the surface. This was direct confirmation of the core collapse theory. Neutrinos from the collapsing core arriving before the light. Exactly as predicted, it was stunning validation and a triumph for neutrino astronomy. Since then, no supernova has been close enough for neutrino detection. Neutrino detectors have become more sensitive. Super Kamiokande, IceCube, others. If a supernova occurred in the Milky Way, we'd detect thousands of neutrinos, maybe millions depending on distance. This would provide unprecedented data. Neutrino arrival times could probe the collapse dynamics. Energy spectrum could reveal core temperatures. Flavor oscillations could teach us about neutrino physics. It would be a goldmine of information. Astronomers wait eagerly for the next galactic supernova, not just for the optical show, but for the neutrinos, the chance to peer directly into the collapsing core of a dying star. Gravitational waves from supernovae are challenging to detect. Unlike neutron star or black hole mergers, which are symmetric and efficient gravitational wave emitters, supernovae are messy. Asymmetric, most of the mass doesn't accelerate coherently, so gravitational wave emission is weak. Current detectors like LIGO and Virgo are not sensitive enough to detect supernovae beyond our galaxy. Maybe not even within it, unless the explosion is particularly asymmetric. But next-generation detectors might succeed. The Einstein Telescope, Cosmic Explorer. These future instruments could detect galactic supernovae, maybe nearby galaxies too. Gravitational waves would arrive within seconds of the neutrinos, before the light, carrying information about the core collapse, the asymmetries, the rotation. Combined with neutrino and electromagnetic observations, this would be multi-messenger astronomy at its finest. 3 completely different messengers, neutrinos, gravitational waves, light, all telling parts of the story. Together, painting a complete picture of a supernova, the chemical enrichment history of the universe is written in supernova. The Big Bang produced hydrogen, helium, tiny amounts of lithium, nothing else. The first generation of stars, population 3 stars, formed from this pristine material. They fused hydrogen into helium, helium into heavier elements. When they exploded as supernovae, they seeded the interstellar medium with the first heavy elements. The next generation of stars, population 2, formed from slightly enriched material, had small amounts of heavy elements, enough to affect their evolution slightly. They too lived and died. More supernovae, more enrichment. Eventually, population-wan stars form, like our Sun, with 1 to 2% heavy elements, enough to form rocky planets, to create complex chemistry, to allow life. Each generation of stars adds to the cumulative enrichment, and we can trace this history by measuring stellar metallicities. Old stars have low metallicity, younger stars have higher metallicity. The Sun's metallicity is typical for its age, and planets in older stellar systems, formed from less enriched material, might be gas-rich and rock-poor, while planets in younger systems might be more metal-rich. This affects habitability. Rocky planets need metals. Complex chemistry needs metals. Life as we know it needs carbon, oxygen, nitrogen, phosphorus. All products of stellar nucleosynthesis and supernovae. The elements created in supernovae tell specific stories. Iron, nickel, cobalt, these iron peak elements are primarily from core collapse and type Ia supernovae. Oxygen, magnesium, silicon from massive star cores before they collapse. Carbon and nitrogen from earlier stages of stellar evolution. Gold, platinum, uranium, the heaviest elements, primarily from neutron star mergers and supernova R-process nucleosynthesis. By measuring elemental abundances in stars and gas clouds, astronomers reconstruct the history of star formation and supernovae in different regions of the galaxy. Some regions have had more supernovae, show higher alpha element enrichment. Others have had more type Ia supernovae, show more iron enrichment. The patterns reveal the galactic chemical evolution, how the Milky Way built up its heavy element content over billions of years. And they vary from galaxy to galaxy. Some galaxies have had different star formation histories, different supernova rates, different enrichment patterns. Studying these differences teaches us about how galaxies evolve, how star formation proceeds, how the universe became chemically complex. Supernovae influence life in subtle and direct ways. The heavy elements they create are essential for life. Carbon, nitrogen, oxygen, phosphorus. None existed in the early universe. All came from stars. Supernovae dispersed them, made them available for planetary formation, for chemistry, for biology. Without supernovae, no life, at least not as we know it. But supernovae can also threaten life. A nearby supernova within 30 light years could damage Earth's ozone layer, bathe the surface in ultraviolet radiation, cause mass extinctions. This might have happened in the past. Some mass extinctions coincide with possible nearby supernovae. Evidence is circumstantial, but plausible. Fortunately, there are no candidate stars close enough to threaten us currently. We're safe. But over geological timescales, nearby supernovae are inevitable. The Sun and Solar System move through the galaxy, sometimes through regions with massive stars, sometimes through quieter regions. We're currently in a relatively safe neighborhood, low density of massive stars. But millions of years ago or in the future, we might pass through more dangerous regions. Life on Earth has survived billions of years, many supernova scares. But perhaps some mass extinctions were triggered by stellar explosions. We're still investigating. The future of supernova astronomy is bright. New surveys are discovering supernovae at unprecedented rates. Automated telescopes scan the sky nightly, compare images to detect new transients. Hundreds of supernovae found every year. Follow-up telescopes observe them in detail. Spectra reveal composition. Light curves show evolution. Multi-wavelength observations from radio to gamma rays paint complete pictures. And theoretical models are improving. Simulations of core collapse require massive supercomputers. But they're getting better, reproducing observed properties, predicting new ones. The interplay between observation and theory drives progress. Each informs the other. Models explain observations. Observations challenge models. We refine our understanding step by step. The James Webb Space Telescope is observing distant supernovae, seeing the universe's first supernovae from population 3 stars. Learning how the earliest enrichment occurred, ground-based telescopes like the Vera Rubin Observatory will discover thousands of supernovae. Monitor them as they evolve. Build enormous databases. Enable statistical studies. Machine learning being applied. Algorithms classify supernovae automatically, identify unusual events, flag candidates for human examination. The field is evolving rapidly. Our knowledge growing. The energy budget of a supernova reveals where all that power goes. 10 to the 46 joules total, about 99% carried away by neutrinos. These neutrinos stream through the star and out into space almost unimpeded. They reach Earth within hours if the supernova is nearby, traveling at nearly light speed. The remaining 1% divides between kinetic energy of the ejector and radiation. The ejector, the star's outer layers blasted into space, carries about 1% of the total energy. That's 10 to the 44 joules in kinetic form. Material moving at thousands of kilometers per second. This kinetic energy will eventually thermalize, convert to heat as the ejector rams into the interstellar medium, creating a hot bubble, a supernova remnant, and a tiny fraction, about 0.01% of the total energy, emerges as light. Photons across all wavelengths from radio to gamma rays. But even this tiny fraction is enormous, about 10 to the 42 joules in electromagnetic radiation, enough to outshine entire galaxies. This is what we observe from Earth, the visible light and other wavelengths. The spectacular display, but it represents less than 1/10,000th of the total energy. Most of the energy escapes invisibly. In neutrinos we can barely detect, and kinetic energy we only see indirectly through the expanding remnant. The diversity of light curves tells us about explosion mechanisms. Type 2 supernovae from massive stars with hydrogen envelopes show plateau light curves. The brightness rises quickly after shock breakout, reaches a peak, then stays relatively constant for weeks or months. This plateau results from hydrogen recombination. As the ejector expand and cool, hydrogen ions recombine with electrons. This releases energy at a rate that keeps the brightness relatively steady. Eventually, the hydrogen fully recombines. The plateau ends. The light curve drops. then rises slightly as radioactive decay takes over. Nickel-56 and cobalt-56 decay powering the tail of the light curve. This lasts for months, gradually fading as the isotopes decay and the ejecta disperse. Type Ib and Type Ike supernovae from massive stars that lost their hydrogen envelopes before exploding show no plateau. Their light curves rise quickly, peak, then decline, powered mainly by radioactive decay, no hydrogen to recombine. Type Ia supernovae show characteristic light curves, very bright peaks, sharp declines, then slower fading. The peak brightness correlates with the decline rate. Brighter supernovae decline more slowly. This Phillips relationship allows standardization. By measuring the decline rate, we can infer the true peak brightness, compare it to the observed brightness, calculate distance. This makes Type Ia supernovae invaluable for cosmology. Spectroscopy reveals composition and velocity. When we take a spectrum of a supernova, we're analyzing the light from the expanding ejecta. Different elements absorb and emit at characteristic wavelengths. Hydrogen produces a series of lines called the Balmer series. Helium has its own lines. Oxygen, silicon, iron all leave fingerprints in the spectrum. By identifying these lines, we determine what elements are present in the ejecta, and the lines are shifted. Doppler shifted, because the ejecta are moving. Material moving away from us shows red-shifted lines. Material moving toward us shows blue-shifted lines. By measuring these shifts, we calculate velocities, expansion speeds of thousands to tens of thousands of kilometers per second. Early spectra show faster velocities, the outermost material moving fastest. As time passes, we see deeper into the ejecta, material that was originally inner layers, moving slower. The velocity profile teaches us about the density structure of the exploded star, how mass was distributed, how the explosion accelerated different layers, and unusual features in spectra hint at asymmetries. If we see blue-shifted absorption without corresponding red-shifted emission, it suggests asymmetric ejecta, material preferentially ejected in some directions. This happens. Supernovae are not perfectly spherical. Rotation, magnetic fields, initial asymmetries in the core all can create departures from spherical symmetry. Dust formation in supernova remnants is a surprising phenomenon. As the ejecta expand and cool, conditions become favorable for dust grain formation. Atoms start sticking together, building molecules, then clusters, eventually solid grains, micron-sized particles of carbon, silicates, iron. We've detected this dust in several young supernova remnants. Infrared observations show the characteristic emission, and the quantities are substantial. Supernovae might be major dust factories, contributing significantly to the cosmic dust budget. This matters because dust plays crucial roles in the universe. It cools molecular clouds, allowing them to collapse and form stars. It provides surfaces for chemical reactions. It blocks and scatters light, affecting what we see. And it's destroyed by shocks and radiation, so it must be replenished. Supernovae provide that replenishment. Each explosion creates solar masses of dust. Some of this dust gets destroyed as the remnant expands, but some survives, mixes with the interstellar medium, becomes part of the next generation of star-forming clouds, and eventually might end up in planets. Earth contains dust from ancient supernovae. Meteorites show pre-solar grains, tiny particles that formed before the solar system. Many came from supernovae. They're recognizable because their isotopic compositions differ from solar system material. They're relics, actual pieces of other stars, and we can study them in laboratories, analyze their structure and composition, learn about the conditions in which they formed. The role of magnetic fields in supernovae is still being understood. Magnetic fields threading the progenitor star can affect the explosion. If the field is strong, it can channel material, create jets, drive asymmetric explosions. Some supernovae might be magnetar-powered. If the neutron star forms with an extremely strong field, a magnetar, it could inject energy into the explosion. Power unusual light curves, create hyperluminous events. Magnetars are neutron stars with magnetic fields of 10 to the 15 Gauss or stronger, 1,000 trillion times Earth's field. These fields store enormous energy. As the magnetar spins down, losing rotational energy, that energy goes somewhere, into heating the neutron star, into powering winds, into energizing the surrounding ejector. This could explain some of the brightest supernovae we observe, events that are too luminous to explain with standard mechanisms. Magnetars might provide the extra energy needed. The connection between gamma-ray bursts and supernovae is established. Some long-duration gamma-ray bursts lasting more than 2 seconds coincide with Type I supernovae. These bursts are the most energetic explosions known. For seconds, they outshine everything else in the universe. The gamma rays come from jets, narrow beams of material moving at nearly the speed of light, punching through the star's outer layers, escaping into space. When a jet happens to point toward Earth, we see a gamma ray burst. The supernova follows days later, the expanding fireball from the broader explosion. Not all Type IC supernovae produce gamma-ray bursts, only a small fraction, maybe 1 in 100. The special ingredient seems to be rapid rotation. If the progenitor star is spinning fast, the collapse can form an accretion disk around the neutron star or black hole. Material swirling inward, heating up, launching jets. These jets carry away energy and angular momentum, allow the explosion to proceed. Without the jets, the star might collapse directly to a black hole, failed supernova. But with jets, you get a gamma-ray burst and a supernova. Collapses, they're called, the most extreme supernovae, rare but spectacular. Computer simulations are essential for understanding supernovae. The physics is too complex for analytic solutions. You need numerical models, solving hydrodynamics equations, tracking shock propagation, including neutrino transport, magnetic fields, nuclear reactions, all simultaneously. These simulations require supercomputers, months of computing time, thousands of processors running in parallel, and even with massive resources, three-dimensional simulations of entire stars are challenging. We're getting better. Modern simulations can follow the collapse, The neutrino heating, the explosion, they're reproducing observed properties. Explosion energies, nickel masses, asymmetries, but some details remain elusive. The exact mechanism by which neutrinos revive, the stalled shockwave, is still debated. Different groups get different results, depending on how they treat neutrino transport, on their assumptions about turbulence and convection, on their computational methods. This is frontier physics. We're probing conditions we can never recreate in laboratories. Densities beyond nuclear, temperatures of hundreds of billions of degrees, enormous energies. We rely on observations to test models, and observations are ambiguous. Each supernova is unique. You can't repeat the experiment. So we compare simulations to populations of observed supernovae, look for statistical agreement, and slowly the picture clarifies. The distribution of supernovae in galaxies follows star formation. Massive stars live short lives. They explode near where they formed. So core collapse, supernovae, trace current star formation. They occur in spiral arms, in starburst regions, wherever massive stars are being born. Type Ia supernovae from old white dwarfs follow the older stellar population. They occur in both spiral and elliptical galaxies, in regions with little current star formation, because the progenitors are old. By mapping supernova locations, we map star formation history, and we see correlations. Galaxies with high star formation rates have more core collapse supernovae. Galaxies with older populations have relatively more type Ia supernovae. This helps us understand galaxy evolution, how star formation proceeds, how stellar populations age, and the rate of supernovae in a galaxy depends on its properties. Luminous galaxies with lots of stars have more supernovae, small galaxies fewer. The Milky Way's supernova rate is about 1 to 3 per century. Andromeda, similar. Small galaxies in our local group might have 1 per millennium or less. Across all galaxies in the observable universe, the combined rate is tens per second. Constant cosmic fireworks. The impact of supernovae on the intergalactic medium extends beyond their host galaxies. Energetic supernovae, especially in small galaxies with shallow gravitational wells, can drive winds. Gas heated by supernovae expands. If it gains enough energy, it can escape the galaxy entirely, carrying metals with it, enriching the intergalactic medium. This is called galactic outflows or superwind. We observe these winds in starburst galaxies, regions where star formation is occurring at high rates, many massive stars forming and exploding. The cumulative effect of multiple supernovae drives gas out. This has important consequences. It regulates star formation, removing gas from the galaxy, slowing future star formation. It enriches the circumgalactic medium, the halo of surrounding galaxies. This enriched gas might fall back later, trigger new star formation, or it might escape entirely, lost to the intergalactic medium, spreading metals across cosmic voids. We detect metals in intergalactic space, absorbing background quasar light, producing absorption lines in spectra. These metals came from supernovae in galaxies, ejected and dispersed, evidence that galaxies are not closed systems. They exchange matter with their surroundings. Supernovae are the mechanism. The effect of supernovae on Earth's history is indirect but significant. We're far from any potential supernova progenitors, safe from direct harm. But over geological timescales, Earth has been exposed to distant supernovae, radiation reaching us after traveling thousands of light years. Probably not enough to cause major damage, but possibly enough to leave traces. Some researchers have looked for isotopic anomalies in ancient rocks and sediments, specific isotopes like iron-60 that are produced in supernovae, but not naturally on Earth. And they've found hints. Layers of ocean sediment containing iron-60, dating to a few million years ago, possibly from a supernova in nearby space. The Scorpius-Centaurus Association, a group of massive stars a few hundred light years away, might have produced supernovae that affected Earth, creating the local bubble, a low-density cavity surrounding the solar system, and perhaps increasing cosmic ray flux, affecting climate, clouds, maybe even evolution. These effects are subtle, hard to pin down, but intriguing. The universe is interconnected. Events far away can have local consequences. The study of supernova neutrinos is neutrino astronomy. Neutrinos are elusive particles, electrically neutral, nearly massless. Interacting only through the weak force and gravity, they pass through normal matter almost unhindered. Trillions of neutrinos from the sun pass through your body every second. You don't notice. They don't interact. But occasionally, very rarely, a neutrino does interact. Hits a nucleus, produces a detectable signal. Neutrino detectors are massive, filled with water or other material, instrumented with sensors to catch the rare flashes of light produced when neutrinos interact. These detectors are typically built deep underground to shield from cosmic rays. And they wait. Most of the neutrinos they detect come from the sun. Solar neutrinos from fusion reactions, or from the atmosphere. Cosmic rays hitting Earth's atmosphere produce neutrinos. But occasionally, from a supernova, there's a burst. Supernova 1987A produced about 24 detections across 3 detectors. Today's detectors are much larger. Super Kamiokande in Japan, Ice Cube at the South Pole, others. If a supernova occurred in the Milky Way, we'd detect thousands or millions of neutrinos, and the neutrino signal would arrive before the light, because neutrinos escape the core immediately. Light takes hours to emerge. This early warning would allow astronomers to point telescopes at the right part of the sky, catch the explosion from the beginning, observe the shock breakout, get data impossible to obtain otherwise. The neutrinos themselves would teach us about the core collapse, about neutrino properties, about physics at extreme conditions. It would be one of the greatest observational opportunities in astronomy, and it's only a matter of time. A galactic supernova will happen eventually, maybe tomorrow, maybe in a century. But when it does, we'll be ready. Detectors are online, monitoring, waiting for that unmistakable burst of neutrinos signaling a nearby dying star. Amateur astronomers play vital roles in supernova discovery. Professional surveys find most supernovae today. Automated telescopes scanning thousands of galaxies nightly. But amateurs still make discoveries. Dedicated observers who know their patch of sky intimately, who notice when a new star appears in a familiar galaxy. The equipment required is modest: a telescope, a camera, software to compare images, and patience. Thousands of hours spent imaging galaxies, looking for changes. When an amateur discovers a supernova, they report it to the International Astronomical Union. Professional astronomers follow up, observe with large telescopes, take spectra, determine the type, monitor the evolution. The amateur gets credit for the discovery, their name associated with the supernova. It's a collaboration, amateurs and professionals working together, and it's accessible. You don't need a PhD to contribute, just dedication and clear skies. Hundreds of amateurs worldwide participate in supernova searches. Some have discovered dozens. It's a way to contribute to science, to be part of the ongoing exploration of the universe, to participate in the discovery process. And when you find a supernova, when you're the first person to notice that a star has exploded, you're witnessing a moment in cosmic history. That star lived for millions of years, and it happened to explode during your lifetime, in the brief window when you were observing. That's remarkable. That's connecting to the cosmos in real time. The future of supernova research includes next-generation surveys and instruments. The Vera Rubin Observatory, coming online soon, will revolutionize transient astronomy. It will image the entire visible sky every few nights, detecting anything that changes. Supernovae, variable stars, asteroids, everything. The data rate will be enormous, millions of alerts per night. Algorithms will filter them, identify candidates, prioritize follow-up. We'll discover supernovae at unprecedented rates. Tens of thousands per year, build enormous statistical samples, understand rare types, probe the full diversity of stellar explosions, and spectroscopic follow-up will improve. New multi-object spectrographs can observe hundreds of targets simultaneously, taking spectra of many supernovae at once, classifying them efficiently, tracking their evolution. We'll characterize supernovas in detail, measure velocities, identify elements, study asymmetries, all in large samples. Statistical studies revealing trends invisible in small samples, and new theoretical tools are emerging. Machine learning algorithms trained on supernova data, able to classify types automatically, predict light curves, identify outliers, interesting unusual events flagged for human examination. The synergy between observation, theory, and computation is driving the field forward. Each decade brings new capabilities, new insights, deeper understanding. The philosophical significance of supernovae extends beyond science. They're reminders of impermanence. Stars are not eternal. They're born, live, die. Everything has a beginning and end. Even stars that shine for millions or billions of years eventually run out of fuel. Collapse, explode. Nothing lasts forever. But the ending is not purely destructive, it's transformative. The star's death creates opportunities, new stars, planets, life. The cycle continues. This resonates with human experience. Endings are also beginnings. Death enables new life, not just metaphorically, literally in the case of supernovae. The heavy elements they create are essential for life. Your existence depends on stellar death, on the fact that stars are not eternal, on the cycle of birth and death operating on cosmic scales. This perspective can be comforting or unsettling, or both. It places human existence in a larger context. We're temporary, fleeting, made of recycled stardust. But we're part of something bigger, a cosmic process that's been ongoing for billions of years. That will continue for billions more. We're links in a chain, participants in the universe's evolution. And that's meaningful, even if we're not permanent. Maybe especially because we're not permanent. Our brief existence is part of the grand story, and supernovae are part of that story too. They're the mechanism that makes complexity and life possible, and understanding them helps us see our place in the cosmos. Temporary but connected, brief but significant, made of stars and capable of understanding stars. That's extraordinary. Supernovae connect us to the cosmos in ways both physical and philosophical. Physically, we're made of supernova debris. The elements in our bodies were forged in stellar cores and scattered by explosions. This is not metaphor, not poetry, literal fact. Your atoms are billions of years old, recycled through multiple generations of stars. You exist because stars died. Philosophically, supernovae remind us of our place in the universe. We're not separate from the cosmos. We're part of it. Temporary arrangements of matter that happens to be conscious, capable of understanding our origins, of tracing the path from hydrogen in the Big Bang to heavy elements in supernovae to planets to life. This knowledge changes how we see ourselves. We're not the center of the universe, not special in cosmic terms, but we're participants. We're the universe experiencing itself, aware of its own history, capable of wonder and curiosity and understanding. That's meaningful. That's profound. Supernovae are not just distant explosions. They're our origin story. They're the mechanism that made complexity possible, that turned a simple universe into a rich one. And understanding them helps us appreciate the grand cycles that shape the cosmos: birth and death, creation and destruction, simple to complex, energy flowing, matter transforming, the universe evolving toward ever greater complexity through the life and death of stars. We're products of that evolution, beneficiaries of billions of years of stellar nucleosynthesis and supernova enrichment. And now we're capable of understanding the process, of looking out at the universe and recognizing our cosmic heritage, of studying the very events that made us possible. That's extraordinary. That's what makes astronomy more than just science. It's self-discovery, understanding where we came from, how we fit into the cosmic story, what the universe is and what we are as part of it. Supernovae give us that understanding. They show us we're made of stars, connected to the cosmos in the most fundamental way. And That's worth celebrating, worth sharing, worth understanding as deeply as we can. Thank you for taking this journey through the life and death of stars with me. And remember that every atom in your body has its own cosmic story, forged in stellar cores, scattered by supernova explosions, gathered into planets, and eventually becoming part of you, aware and capable of understanding the magnificent universe that created you.